Hey guys, we are the group for containerizing neural network apps for medical compute. Our group members are Brian, which is me, Ken, Tingy, Kagri, and Xiaoyu. Our mentors for the project are Rudolph and Sandeep. So, what's the problem? Over the past few decades, there have been a tremendous amount of work done in the area of computational medical research. Researchers use image processing, machine learning, and neural networks to determine certain patterns in diseases. However, we can question the practical impact of these improvements. The lack of easy access to data and computational power became the largest obstacle for non-technical users. So the overall goal is to develop an application that can perform medical computations without extreme hardware on a local computer. The application must also be user-friendly. So the Fetal Neonatal Neuroimaging and Development Science Center, or FNNBSC for short, has created CRIS, which is an open source platform with a web GUI that uses cloud technologies for medical application development. CRIS is the solution for Boston Children's Hospital's problem. CRIS was developed for clinical users who want easy access to both data and computation results. CRIS achieves this goal via the use of plugins and pipelines, which are a set of plugins, which can perform medical level computations specific to the user. The pro of this method is that CRIS is very modular, and these plugins and pipelines can be made to handle as specific of an instruction as needed. However, this is also a downside, as plugins and pipelines will consistently need to be developed to handle more and more different types of instructions. So more generally, this is the architecture of CRIS. So starting at the top, the CRIS backend and frontend can be either installed on a local machine or at an institution. CRIS UI can then be accessed. Data computation, including I/O handling and process management, is done in the cloud. Specifically, OpenShift will handle the use of plugins, and OpenStack will manage the storage of inputs and output data. So we've talked about the overall problem and plan for Boston Children's Hospital, and we've also talked about the solution, CRIS. However, we haven't talked about where the project is at. CRIS is still ongoing in the development of the front end and back end, and with the UI and GUI. CRIS is also ongoing in development of main plugins and workflows, and still in development stage with the use of cloud. So now we can talk about where we come in, or our group. Our project will be to create a specific pipeline that converts brain MRI images to volume text reports that specify how much volume a certain part of the brain is. Our project also consists of putting together the CRIS workflow on Mock specifically and running the developed plugins. So here's our MVP in more specifics. To achieve a pipeline that converts brain MRI images to volume text reports, we need two pipelines. A training pipeline that will train a model that can predict the segmentation of a brain, and another pipeline that uses the model developed in the training pipeline to predict the segmentation of the brain. Our mentors have yet decided which classifiers work best to train a model, so we will be testing the use of one classifier to identify all parts of the brain, and another that utilizes multiple classifiers to identify specific parts of the brain, and that will accumulate to all parts. Then we will need an inference pipeline that uses the model from the training pipeline to predict the segmentation of the brain and put the volume of these segmentations in a text report. I want to emphasize that we were given a lot of these plugins already, but our main goal is to create the workflow that utilizes these plugins. We will speak about the specifics of what plugins were given and what work we've had to do later on. Now, as stated previously, we will be putting together the CRIS workflow on Mock and running the development and running the developed plugins on Mock. Sorry, the cloud technologies for CRIS have been developed but have not been tested, and we will be the ones to make sure the workflow runs on the cloud. We will talk about what we've had to develop, change, and debug later on. So generalizing our goals, basically we will create an assembly line. So essentially we are given the robots that assemble the package. Our object is to put these robots in a specific order that give us the deliveries we want. We need to make sure the output of a robot are designed so the next robot can accept it. We need to make sure the runway for the assembly line is accurate so these packages can go from robot to robot. And finally, we need to test the assembly line.
Okay, I'm going to introduce our pipeline. First, I'm gonna talk about what existed Chris plugins we are using our pipeline. The start point of pipeline is a Chris plugin called PL third copy, which upload files to Chris. And there are two existing plugins that can consist of our first training pipeline, MGZ converter and MRICNN. So MGZ converter is a Chris plugin that convert MGZ files to PNG images. And MRICNN is a 3D unit for image segmentation. MRICNN will output .h5 models that will be used for inference. And the MGZ converter and MRCN plugins are our first training pipeline. So the plugin we've built in the training pipeline are MGZ2 labels and NMR unit SCR. They will be introduced later. So for the inference pipeline, the first step of our inference pipeline is still third copy. Then we use a Chris plugin called Met to Image to convert DICOM to images, then feed images into neural network plugin MRCNN. The current plugin MRCNN can only inference using one model at a time. That is enough for our first inference pipeline, which is segmentation on the whole brand. What we've built are MR unit SCR and image to report plugins, which will be introduced later as well. Next, please. Okay, let's talk about what we've developed. We complete our MVP, which is generate text report from brand images. We've built 4 plugins. The first one is MGZ2 labels that convert MGZ files to images of separated labels of the brand. The second one is MRI unit SCR. SCR is for serial, which is kind of an automation tool for training and inference. It is designed to dock the output of MGZ2 labels. The third one is image to report. They convert segmented images to volume text report. And last, we also build a heat map plugin to compare the prediction and the ground truth. More importantly, we deploy our plugins on both MOC and Chris platform, and they will be demonstrated later. Next, please. So let's review our entire workflow. We have 2 pipelines. Pipeline number 1 is for the classifier that segments the whole brand. The inputs are MGZ files, and MGZ converter convert input to PMG images and feed into MRICN plugin for training and output 3D unit models. And for inference, the input DICOM will convert to PMG files using Met to image and using MRICN plugin to predict segmentation with the model we train. Last, feed the segmented images to image to report plugin and output text report. And pipeline number 2 is for classifiers that focus on a specific region of the brand. This is the pipeline we focused on. The training workflow of this pipeline is that we convert MGZ files to images of all labels using MGZ2 labels and feed all these images into MR unit SCR at once for training. And after training, we will get about 190.5 models. The inference pipeline is pretty much the same as the first pipeline, except that we need to put all the segmented labels together into images of a whole brand. Next, please. Okay, that's the result of our heat map plugin. This plugin is kind of a bonus plugin. It's not part of our MVP. It is very useful for comparing between the ground truth and inference images, which help us to understand the accuracy of our model in a human readable way. So that's all our plugins and the entire workflow.
All right, so now we're just going to demo the training pipeline number 2, training multiple labels on the Chris UI. Okay, now I'm going to demo our second training pipeline using the UI. This pipeline will train many models on individual labels as opposed to one model with multiple labels. So first, to get the UI up and running, I have on the left created an instance of the Chris backend. Once that container is deployed, you can create an instance of the Chris frontend in another shell. Now that the backend and frontend are deployed, we can see that they're deployed in our Docker dashboard as both are running. We can navigate to the backend and start our feed. So there are a few options to start a feed. Every feed starts with a feed synthesis plugin. This will be our starting point for running our plugins. For this demo to start our feed, we'll push our local dataset to the backend Swift storage. We'll run our first feed synthesis plugin from the backend and then continue with the rest of the pipeline on the front end. So here we have navigated to the directory of our backend. We can upload our first dataset to Swift storage and then run our feed synthesis from there. So first, we'll push our dataset into Swift storage. You can see that we pushed one dataset from one patient with 2 MGZ files into Swift storage. So now from the back end, we'll also run our first feed synthesis plugin to get our feed started. Okay, we get the JSON response, which means it was successful. So now we can move to the UI and check on our feed. All right, so this is the feed that we just started. You can see it was last committed a few seconds ago. So basically this feed, we can see our node, our data is transmitted, it's setting up the compute environment, and from there we can continue our pipeline. So now that we see our data successfully computed its feed synthesis plugin, we see our metadata, our single patient directory with 2 MGZ files. So now we can utilize our next plugin by adding a node. And for this training pipeline, our second step is going to be this MGZ2Labels plugin. So again, MGZ2Labels will separate the MGZ files into training sets, masks, and 2 NumPy files for each label. So we can go ahead and execute that. And once it starts computing, we can check the logs and make sure it's working. We can see the plugin started, and it's now creating the training images and the masks. Processing for one subject. This may take a moment, so we'll come back once it's finished. Okay, so now we can see that the process has separated the MGZ files into many labels and is finished. So if we go up, we'll see that our compute finished and now the data is syncing. Okay, now that PL_dir copy has finished successfully, our second node, MGZ2Labels, has finished successfully, we can now add our third and final node, PL MRI UNet SER. This is a training model that will train all the 194 labels from MGZ2Labels. So for this mode, we can choose one for train and click next. We'll add this node. This will take a little while, but once the data transmits, the training will begin on each individual label for our patient. Our MRI UNet SER has transmitted the data, set up compute, and is now computing. We scroll down and look at the logs, and we see that the model is being built, it's being fitted, and it's starting to train on the epochs.
Now I'm going to be talking about the CRIS architecture on MOC. To go over it briefly, we have our local machine at the top, following with an I/O handler called Pifia, which is a service that pushes and pulls files and directories between our local machine and OpenStack Swift storage. On the left, we have our Swift storage that stores files, directories, or even containers on OpenStack. On the right, we have our process manager called pman, which is another service for executing, killing, or checking the status of the processes. We're going to see how these services interact with each other in detail in the demo video. Before that, I want to clarify a couple of things. Next slide, please. Next. Okay, first of all, Pifia and pman are services that were already built and tested by the FNNDSC team in the past. By the time we started this project, those services weren't working properly on MOC. We had to go back and forth with the team to troubleshoot these problems. We had bad requests, unauthorized requests, invalid responses, and much more. This proves to be a very tiresome and daunting task, as errors either come from the services, our local computer, or even MOC. So tracking them down wasn't that easy. Fortunately, with determination and perseverance, we were able to overcome these issues before Sprint 5 and started testing the plugins we have developed on MOC. Next slide. This is a picture that shows Pifia and pman running on OpenShift after we troubleshoot the problems. Next slide. Now we're going to see the inference plugin running on MOC. Okay, let's start with pushing the necessary files to OpenStack in order to feed it to our plugin. For this, we're going to run our script called run pifia push with specifying our container name as job ID 528. We can see our I/O handler and process manager deployed on OpenShift. Let's take a moment to look at Pifia's logs. We can see that the request is received and the upload process has started. This process is going to take a while depending on the file size. Fast forwarding this process, we can infer that the operation was successful looking at the JSON response. Let's head to OpenStack and refresh the page to see if the container is created. We can see our container name and the files uploaded to the input directory. It's time to run our plugin MRI unit for inference. This time, we're running the script MRI unit with specifying the same container name. We can see that our pod is initializing. Let's check the events if there's anything wrong. It looks like everything is going smoothly. We can also see that the pod has successfully bounded with storage. It looks like our plugin is working fine. Our plugin is predicting masks using the weights we obtained from training the model. After predicting the masks, it's going to output images and a NumPy file and store it on OpenStack. Okay, our images are created and the prediction is done. Let's go back to OpenStack and refresh the page to see if we have the output. We can switch back to our local machine to pull the results. We're going to use the script run pifia pull with specifying the same container name and a target directory to store the results. On the process manager, we can see that the request has received and the download results generated. Okay, it looks like the pull is successful. Let's head to the directory that we pulled the results. We can see the image directory for the masks and the NumPy file. Let's take a look at one of the masks. And here is a predicted mask for one of the images. This was inference on MOC.
Okay, so let me talk about what we have learned in this project. In this project, we built some small scripts at the beginning and keep adding features to existing plugins, and eventually we built a whole pipeline. I think we carried the agile method through the entire project. And also, this project looks like a machine learning project, but it is not. What matters in this project is the pipeline, which is about putting different components together to generate the result we want. With this pipeline model, intermediate results are reusable. For example, in our pipeline, the pre-processed brain image can be fed into other machine learning programs. Also, one important tool we use is Docker. It plays an important role in deploying our plugins to the cloud platform, like Chris and MOC. With Docker, your program can run in basically any operating system, which makes developers focus on coding instead of the environment. What's more, we encounter tons of issues when we tried running containers on Mock or Chris. Some of the problems came out from nowhere and cannot be solved by just reading the documents. So we need to consult with our mentor and staff at MOC. One thing we can learn in this process is how to describe our technical issues precisely so that other people can help us debugging, which is very important in a real industry working environment. It is not easy for us to finish a project like this. In the beginning, we have a tough time understanding the whole project. Which existing plugin can we use? What features are we going to add? We are a little bit off track when we start, but thanks to our mentors who pull us back on the right track. Besides, our mentor travels to South Africa in the last few weeks, so the communication between us is delayed. But anyway, this project is fairly well done. Next slide, please. So for this project, we built two pipelines, one classifier for the whole brain, another classifier for each label. But we are not able to train models for all the labels because of time limitation. It would take about a month to train all the models. And also, the prediction result of our current model is not 100% accurate, but all the components are set. With more time, we can train models with more data and compare the performance between those two types of classifiers. Our original plan is to use our inference plugin to segment all labels and put them together as a whole brain to generate a text report and compare the result with the first type of classifier. We expect this result would be better. It is a pity we can't see this happen. And also for now, we only explore a small portion of resource on MOC and Chris. We can only use this for a simple demo. In the future, it would be great if we can fully utilize the computing resource on MOC and Chris and truly deploy our plugin up to the cloud, which will make clinical users do medical analysis job in a much easier way. Thank you.